Hello again, everyone. Today, we're going to move on in the redox unit, and we're going to do something that's called half reactions. So remember what we're dealing with in redox. That's our contraction for oxidation reduction reactions. You have both of these processes happening at the same time, oxidation and reduction. So remember what these are. Leo says GER. So a loss of electrons is oxidation, and a gain of electrons is reduction. And you have both of these happening at the same time. So in a redox reaction, you have that movement of electrons taking place. So what is a half reaction? It's exactly what it sounds like. It's showing only half of the reaction. So it's showing either the oxidation or the reduction portion of the reaction. So this topic is very cumulative, as I've said before. So it's kind of everything that we've been doing together, and we just keep building upon previous concepts and building and building. So that's pretty much what we're doing today. So we're going to use this problem as an example. So take a second, write this down, and then we're going to go through all of our steps. So the first thing you want to be able to do is to do what we've been doing so far, is to figure out who's oxidized and who is reduced. So step one, assign oxidation states. So we go through and give everybody oxidation states. Remember, your uncombines get zeros. So Mg and hydrogen get zeros. And then everybody else we figure out. All right, so we know hydrogen is usually +1, which means chlorine has to be -1. If you don't need to make the table anymore, you can do it in your head at this point. That's great. So for the next one, we know Mg is +2. So if you need to make the little table, figure it out, right? If not, that's great. So we need -2 to get to 0. So that means chlorine gets the -1, right? So -2 divided by 2 is -1. So get all the oxidation states. And now the next thing we want to do is connect the ones that changed. So Mg went from 0 to +2, and hydrogen went from +1 to 0. So remember what we do now is we write over these bridges how many electrons were lost or gained. And if you've been doing that all along, that's great. It hasn't really helped you out so far, but now is when that will pay off. So you'll have been building good habits. So Mg0 lost 2 electrons. It went from 0 to +2. Remember, Leo jumps up. So when you're going up in oxidation state, you're losing electrons. And hydrogen went from +1 to 0, which is a gain of 1 electron, right? So and hydrogen went from +1 to 0, which means it gained 1 electron. Because remember, when you're gaining a negative electron, your oxidation state is going to go down. So, right, you're gaining negatives, so your oxidation state is decreasing. So now what? Now we can figure out who's oxidized and who's reduced. So let me erase. Let me get rid of this so we can see here. So now we use our Leo says GER. Whoever lost was oxidized. So Mg0 is oxidized, and whoever gains is reduced. So H+1 was reduced. So remember, we're always taking off of the left-hand side. So where the reaction is taking place, the reactant side. So Mg0 is oxidized, H+1 is reduced. So we're always getting our oxidized and reduced species, right? Remember what the species is, the element and its oxidation state. Those are always coming off of the left-hand side. So that's everything that we've done already. So nothing new. But now we're going to build upon that and write our half reaction. So write this little table down, and we're going to go through and write each half of the oxidation reduction reaction that's taking place individually. So let's do oxidation first. So I just moved it up a little bit so you can see it better. So Mg0 is oxidized. So what does that mean? So Mg0 is becoming, so we draw arrow. So you kind of think of it as you're pulling, So let's take a look at what's going on here. So oxidation Mg0. Mg0 is oxidized. We figured that out already. So we're kind of taking just the oxidation portion out of the entire reaction. So Mg0 is becoming Mg plus 2. So we want to show that, right? Mg0 is becoming, arrow, Mg plus 2. So we're just kind of pulling these out of the whole reaction and making just the oxidation portion. Now, what is going on when it's becoming Mg plus 2? It's losing 2 electrons. So remember what's going on here. When electrons are lost, just like when energy is lost, the electrons are leaving, right? They're leaving. So Mg0 is becoming Mg plus 2 plus the 2 electrons that it lost, right? So it lost 2 electrons. So think of it as the electrons are leaving. You're losing electrons. Just like an exothermic reaction, when you're losing energy, the electrons are exiting. They're leaving the reaction. They're on the right. So same thing with these electrons here. So think about those concepts that we've done in the past and how those rules stay the same and apply elsewhere. So now, who gained? H plus 1. So now we're going to take that portion of the reaction and pull that out separately as well. All right, so now H plus 1, here it is becoming H0, right? But remember what H plus 1 is doing. It's becoming H0 by gaining an electron. So just like when you're gaining energy, the energy is entering the equation. Same thing here. When you're gaining electrons, the electrons enter the half reaction. So they're going to be on the left-hand side. So H plus 1 gains 1 electron, right? We figured that out already. So this is where that part pays off to become H0. So all we're doing is we're pulling the reduction portion out of the reaction. So here's the arrow. So H plus 1 is on the left. That's the same. H0 is on the right. That's the same. So don't worry about the subscript, right? Keep it simple. This is the easiest way to do it. Just bring down individual atoms or ions. That's the easiest way to do it. Now, when it's a Brinkelhoff, we'll talk about that in a second, but for now, let's keep it simple. All right, so remember, oxidation is a loss of electrons. Electrons are leaving. They're always going to be on the right-hand side. They're exiting the equation. So electrons are always on the right. So think about it as lost equals leaving, right? Just like with energy. Energy is lost, it's leaving, it's on the right-hand side, right? And then for reduction, the electrons are always on the left, because when you're gaining, think about it as the electrons are entering, right? We're gaining, they're coming into the equation. They're going to be on the left-hand side. That's it. So the hardest part here is just putting the electrons on the appropriate side, right? And whether we're gaining or losing, we're always adding. Just like with energy that we've done before, it's always adding. It's just a matter of which side the energy goes on. Same thing here. When we're losing electrons, they go on the right. When we're gaining electrons, they go on the left. It's that simple. So now the next thing is, let's just talk about the Brinkelhoffs for a second. So you can, when it's a Brinkelhoff, show the two atoms in the diatomic stuck together, and that would look like this. So just write this down and have that as a reference, because you can see that given to you as an option for a multiple choice question or whatever. But when asked to draw a half reaction, always do this. Keep it simple. One atom, one ion, whatever, because then you got to account for the number of electrons for each atom that you're incorporating into the half reaction. So it's not as simple as just putting that subscript in. Then you have to have each hydrogen is gaining 1 electron. So there's 2 hydrogens. So there's 2 electrons gained. This is confusing. All right. So just keep in mind, any Brinkelhoff can be shown as diatomic in an uncombined state. All right. But don't draw it like that. If you're asked to draw a half reaction, keep it simple. Right. This is what you want to do. Do this. When they ask you to draw a half reaction, that'll always be right. This is right too, but it's harder. So you're putting yourself out there to make another mistake, and we don't really need that, right? So that's really pretty much it as far as new material goes for today. So all I want to do now is practice. So let's take a look at some practice problems. This worksheet is attached to the lesson if you want to download it and open it on your tablet or whatever, or print it out, whatever works for you, or write it down on a piece of paper. You know what to do at this point. So if you're still a little confused, watch the first one with me and then try the other ones on your own. All right. If you think you got a pretty good handle of it now, try the first one and then unpause the video, see if you got it right, and move forward. So kind of do that step by step going through these problems, and we'll go over them. So based on how well you understand this concept, go ahead and try them on your own, or keep watching the video, see how I do the first one, then pause it, work on another one. Number 2, we're going to skip. All right, so make sure you skip number 2. Write that down on the sheet. Skip number 2. Don't do that one. So we're going to do everything else but number 2. So number 1, first thing, assign oxidation states. So everybody gets an oxidation state, and we want to figure out who's oxidized and who's reduced. So same thing we've done before. Who's oxidized, who's reduced. So how do we do that? Give everybody an oxidation state. So uncombines get zeros. Put those in first right away. Okay, now for the next one, CuCl2. So remember our rules. Chlorine is a halogen. So we know our fluorine is always -1, but our other halogens, depending on where they are, they could be -1. And in this case, when they're on the end, they're -1. So chlorine gets a -1. And then that means if you got to make your little table to figure things out, go for it. If not, you know what to do. So we're going to end up with copper as +2, right? If you had to make your little table, equals 0, -1 times 2 is -2. So +2, there's only one copper, so it gets the +2. So if you got to make the little table to figure it out, draw it right into the equation, and you'll be fine, right? And then same thing over here. Chlorine is -1, but we also kind of know that zinc is going to be +2 because when we look on the periodic table, it only has one choice, and we can usually use that one choice when that's our only option, right? So we've assigned oxidation states to everybody. So let me get this out of our way here. We've assigned oxidation states to everybody. So now what we want to do is connect the ones that changed, all the same stuff we've been doing. So zinc went from 0 to +2, and copper went from +2 to 0. So let's write in what happened in terms of the loss and the gain, because that's going to help us write the half reactions. So zinc lost 2 electrons. It went from 0 to +2. And copper gained 2 electrons. Went from +2 to 0. So now we use good old Leo Szesger again here to help us figure out who's oxidized and who's reduced. So zinc 0 lost, so that means we were oxidized, and copper +2 is reduced. So nothing new. That's everything we've done before today. So now we're going to complete the half reactions. All right, so that's the last step that I want you to do. That's new. That's what we did today. So zinc 0, so you're pulling that half, that lost half of the reaction out of the equation. So zinc 0 is becoming zinc +2 by losing 2 electrons. So zinc 0 becomes zinc +2. So you're pulling them right down. So they're staying on the same side of the arrow as they are in the original equation. Zinc 0 on the left, zinc +2 on the right. And now we're just adding in the electrons. So we're losing, so electrons are leaving, so they go on the right. So those +2 electrons go on the right. All right. Copper is gaining 2 electrons to become copper 0. All right. So once you're done, you've gotten your half reactions here. So that's all you're really going to do is get those 2 half reactions. Once you have an oxidation half reaction and a reduction half reaction, you're done. So zinc 0 is becoming zinc +2. You can check to see if you did things correctly by seeing if the charges are equal on both sides of the half reaction. That shows us that we're dealing with a balanced half reaction. So that shows us that we're dealing with a balanced half reaction. So that's where the total charge on the left equals the total charge on the right. Okay, so what do? We just check, all right? So here we've got zinc 0, 0 on the left, right? So plus 2 and 2 negative ones is minus 2, plus 2, minus 2, 0 on the right. So we've got 0 on the left, 0 on the right. We're good. So that's kind of a good way to check, because if you put the electrons on the wrong side, those charges aren't going to add up and be equal on both sides. All right. Same thing with the reduction reaction. Plus 2, minus 2, 0, 0 on the right. We're good. So that's a good way to kind of check when you're done and see if things work out. All right. So next one. First off, assign oxidation states. So I just did it quick here. So plus 3, minus 1, blah, blah, blah. So who changed? Iron went from plus 3 to 0, and zinc went from 0 to plus 2. So whoever jumped up, right, Leo jumps up, lost. So zinc 0 lost 2 electrons, and iron gained 3. Right? So now we add that down here. Zinc 0 is becoming, zinc 0 is oxidized, and iron plus 3 is reduced. So Leo says Gur. So zinc is becoming zinc plus 2 by losing 2 electrons. So the electrons go on the right. They're exiting the equation. They're lost. They're leaving. And then iron gains 3 electrons to become iron 0. And again, you can check to see if your total charges match up on both sides to kind of make sure that you did things correctly. So 0 on the left, plus 2, minus 2, 0 on the right. It's not always going to add up to 0. They're just going to be equal. So a lot of times they do add up to 0, but it doesn't always have to be 0. Plus 3, minus 3, 0, 0. All right. Number 4, check this one out, see how you did. Connect the ones that changed. Aluminum lost 3 electrons, chlorine gained 1. So Al0 is oxidized and chlorine 0 is reduced. So aluminum is becoming aluminum plus 3 by losing 3 electrons. And then chlorine is gaining 1 electron to become chlorine minus 1. So now the electrons lost and gained don't have to match up at this point. We're going to get to that when we balance these redox reactions later on in the unit. So don't worry about that right now, but this is going to help us going forward to the next step. All right. So again, this unit, everything builds off of what you've done before. So you want to make sure you really understand each part well. Number 5, assign oxidation states, connect the ones that changed, who lost, who gained. So O minus 2 is oxidized because we lost, and then Hg plus 2 was reduced. And then O minus 2 is becoming O0 plus the 2 electrons that it lost. And then H is gaining 2 electrons to become Hg0. And then the last one, assign oxidation states, connect the ones that changed, who lost, who gained, and then who's oxidized, who's reduced. So S plus 4 is oxidized and O0 is reduced. And then we want to write our half reactions. So S plus 4 is becoming S plus 6 by losing 2 electrons. And then oxygen is gaining 2 electrons to become O minus 2. So now remember, we can check to see if our charge is equal on both sides of each half reaction. And this is a good example where you'll see they don't have to add up to 0. So S plus 4. So we've got plus 4 on the left, plus 6 plus 2 negatives. So adding a negative is subtraction. We've got plus 4 on the right. So again, they don't have to be 0, but they are equal. Same thing here. 0 plus 2 negatives is minus 2. Minus 2 over here. So that's a good way to check, because if you put your electrons on the wrong side, the charge on each side of the half reaction isn't going to match up. So that's just kind of a good safety to check at the end. All right, so that's it for today. If you did all right, you were able to do everything on your own, and you did it well, and you checked it, and you got everything right, then you're doing great. I'll see you next time.